Today's topic is diagonalizability. The minimum requirement to understand this topic is basic linear algebra. Well, the contents. So whatever we cover here that basically answer three fundamental questions. What is a diagonalizable matrix? How to examine diagonalizability? And why do we study it? So what is a diagonalizable matrix? So throughout this discussion, we consider only square matrices. So before come to the notion of diagonalizable matrix, we need to know about what are the similar matrices. So two matrices A and B are similar if one of them can be decomposed into other. Like here A is similar to B if we can write A as P inverse BP for some invertible matrix P. Now, what is a diagonalizable matrix? So a matrix A is diagonalizable if it is similar to a diagonal matrix D. That is, A is diagonalizable if and only if we can decompose A as P inverse BP for some invertible matrix P and diagonal matrix D. And in that case, this decomposition A is equal to P inverse dP, this decomposition is known as a spectral decomposition of A. Well, now we analyze diagonalizable matrices. Well, as of now, we know that A is diagonalizable if and only if we have this decomposition. But in this decomposition, what are P and D? How to get them if they exist? Now we look into this definition. P inverse AP is equal to D. That is, AP is equal to PD. So if we write P as its column form, like here C1, this is the first column of P, C2, this is the second column of P, and Cn, this is the nth column of P, then in the right hand side, we can write P times some diagonal matrix D, and here I am writing D1 as the first diagonal entries of the matrix D, and Dn, this is the nth diagonal entries of the matrix D. Now, if we multiply left hand side and right hand side, then we basically get these two matrices. So in the left hand side here, the first column is nothing but A times C1, and the second column, this is the A times C2, and the nth column is the A times Cn. And in the right hand side, first column, we can see this will be nothing but D1 times C1, and so on. The nth column, this will be nothing but Dn times Cn. As these two matrices are same, so their corresponding columns are also same. So if you compare each column, then basically we get A times Ci is equal to Di times Ci. So here I runs from 1 to n. So what is that? That means Di, this is nothing but an eigenvalue of the matrix A, and with an associated eigenvector is Ci, right? Now, as this matrix P is invertible, that is all these columns C1, C2 up to Cn, they are linearly independent, and now we know that Ci's, they are nothing but the eigenvectors. So basically from there we can say A has n linearly independent eigenvectors. That is very important. So now in this way we can define diagonalizability. We can give another alternative definition of diagonalizability. What is that? That means a matrix A is diagonalizable if eigenvectors of A forms a basis, or we can say A has n linearly independent eigenvectors. So what is P and what is D? So here P, this is formed by the linearly independent eigenvectors, and D, this is formed by eigenvalues. And how they are related? Like here D1, this is an eigenvalue and its corresponding eigenvector is C1. Okay. Now we come to the next question, that how to examine diagonalizability. So here the first computational way is by definition of course. So first we compute all eigenvalues of A and their corresponding eigenvectors. If the number of linearly independent eigenvectors is n, then by definition we can say A is diagonalizable, otherwise this is not diagonalizable. So this is by definition. So other way, if we know some of the fundamental results, then using that results we can also examine diagonalizability. So suppose we have a very nice result. It says that all real symmetric matrices are diagonalizable. That means whenever we see any real symmetric matrix, then instantly we can say, yes, it is diagonalizable due to this result. Okay. The another result says that A is diagonalizable if and only if its minimal polynomial splits into distinct linear factors. Remember that distinct is very important here. Well, I'll explain one example. So here we have one example. Suppose A and B, they are two matrices of same order and we know their minimal polynomials. So this is the minimal polynomial of A and this is the minimal polynomial of B. Then by looking into their minimal polynomial, we can instantly say that A is diagonalizable and B is not diagonalizable. So why A is diagonalizable? Because its minimal polynomial splits into two distinct linear factors. Then by result 2, we can say A is diagonalizable. And why B is not diagonalizable? Because it is clear that that the minimal polynomial of B splits into three linear factors, but among three linear factors, two are same. X minus 6 times x minus 6. So these two factors are equal. So that's why by definition, by result 2, we can say B is not diagonalizable. Well, come to third result. It says that if a matrix A has all distinct eigenvalues, then we can say A is diagonalizable. So suppose we have one example, A is equal to this matrix, and one can ask about its diagonalizability. Then we first find out its eigenvalues. As all eigenvalues are distinct, so by result 3, we can simply say A is diagonalizable. Okay, now we come to our final section. So why this is important? Now here I present one example of a linear operator from R3 to R3. Then what are the basic questions one can ask about a linear operator? So these are like, what is the rank of this operator, nullity of this operator, and two very important subspaces associated with a linear operator. They are the range space of T and null space of T. So to answer this kind of question, sometime we look into its matrix representation and compute these values from its corresponding matrix. Now, if this operator is diagonalizable, then we know its matrix, then we know there is at least a diagonal matrix which represent this linear operator. So here in this pictorial view, we can see T, this is our linear operator, and as it is diagonalizable, so it is represented by a diagonal matrix, this, by an ordered basis beta 2. So beta 2, there will be nothing but the eigenvectors actually. So now by looking into this matrix, we can instantly answer all these questions. Like what is the rank of this operator? And it is nothing but the number of non-zero diagonal entries of this matrix. And here it is 3. So therefore the rank of this operator is 3. And what is the determinant of this operator? And which is nothing but the product of the diagonal entries. And therefore it is 126 and so on. So the another advantage is that the computations of any power of A, for example, a to the power k. If our matrix is diagonalizable, then we can instantly compute its power like this way. And also we can compute e to the power A type of matrix. So these kind of matrices are very important in computation of the solution of system of linear differential equation. So these are some of the application of diagonalizable matrix.